So for last lecture, we had an introduction, right, where we talked about overview of the class, modeling and simulation of multidisciplinary systems. Now today we are going to go a little bit over compact modeling and simulation of ODEs. I did find out from IT that they are actually installing CompSol right now, so we should have it up and running by our next meeting on Thursday, or if not, then next Tuesday. Okay. Oh yeah, and Matt's recording lectures, as you guys know. He put the lectures right here, so here's the link, and I'll be putting all the lectures online on campus. So you just click on that link and see the videos if you guys need to do that. Okay, so topics for today: compact modeling, compliant mechanisms, MIMS, microelectromechanical systems, which are actually compliant mechanisms, right? But there's really interesting things that happen with MIMS, and we'll talk about that, dealing with the scaling laws. Quite interesting things. We'll talk about a brief overview of how MIMS are made, for those of you who don't know, just to get a brief overview of that. And then we'll get into compact modeling of MIMS, an overview of a tool that I created called SugarCube. Then we'll talk about the cantilever and how cantilevers add their stiffnesses, looking at the mass. And then we'll look at ODEs and how to simulate ODEs in MATLAB. Okay, so first of all, for compliant mechanisms, that thing's better than a great video. So let me show this video right there.
This satellite thruster, plastic tool,
Can you guys hear
and
this in the back?
micromechanical switch have in common?
Great.
Well, they all
Okay.
contain components that bend, so-called compliant mechanisms. This episode was sponsored by SimpliSafe. More about them at the end of the show. Now, about a month ago, I was giving a talk in Utah, hence the suit. And that's where I met this guy.
Larry Howell, professor of mechanical engineering. So it's always been considered to be bad to have flexibility in your machines. Well, we've tried to take that thing that everybody hates and is trying to avoid and say, how can we use flexibility to our advantage? How can we use that to do cool stuff?
Now, Professor Howell literally wrote the book on compliant mechanisms.
That's the most cited book.
But he's pretty nonchalant about his work. Just watch how he introduces this mechanism he developed to prevent nuclear weapons from going off accidentally.
Actually, a safing and arming of nuclear weapons. And so
What?
if you want to
Hang on. What are nuclear weapons?
safing and arming. So,
Safing and arming.
yeah, so if there's anything in the world that you want to be safe that is not going to accidentally go off.
I feel like it doesn't even need saying, but yes, nuclear weapons, obviously you don't want them to go off. Well, I don't understand how this is going to keep a nuclear weapon safe.
Now, I want to come back to this device and explain how it works, once we understand why compliant mechanisms are best suited to this task.
That's cool.
So let's start with
And we'll be
something
doing
basic.
lots of
Probably the first
mechanisms in
compliant
CompSol.
mechanism I ever designed was this thing. What it is a compliant mechanism that is a gripper. So you can put something in there and it'll get actually a really high force. I can put that in there and it breaks the chalk.
What if you put your finger in there and squeeze it?
You would scream in pain. Would you like to try?
I would.
Okay.
Like, I would actually like to feel the force.
Okay. You need to squeeze it yourself, though. Or
Really?
Well, all right. I'll squeeze till
But,
you
like,
scream
don't-
in pain.
That very quickly got incredibly painful. It felt like having my finger like in a vice.
That looks suspiciously like vice grips, but now with these flexible components where the hinges are.
What I learned in my visit with Professor Howell is that compliant mechanisms have a number of advantages over traditional mechanisms. But I thought he needed kind of a clever, pithy way to remember all of these advantages. So I came up with the 8 P's of compliant mechanisms. And the first of those is part count. Compliant mechanisms have reduced part count because they have these bendy parts instead of having things like hinges and bearings and separate springs. This gripper is just a single piece of plastic, but achieves a similar result to the much more complicated vice grips.
Like, how much does it amplify the force?
This will get about 30 to 1. So I could get, for 1 pound force in, get 30 pounds out. So
That's pretty good.
Yeah.
It seems like that would be super cheap.
and really inexpensive. So this we just made here in our shop, but you can imagine also injection molding that.
That would cost like cents.
Yeah, this would cost cents. Another thing is, because of its shape, you could extrude it and then just chop them off. That would be cool.
So the simple design allows different production processes to be used, which lowers the price. These switches, for example, achieve in one piece of plastic what is normally done with springs, hinges, and many rigid plastic pieces.
Also a good fidget device.
How long can these last?
We've had these in our fatigue testing machine. We've been able to go over 1 million cycles without failure.
What do we got there?
All right, Derek, I've got a quiz.
Uh-oh.
Quiz for you. Okay?
Elephant.
This is very good. Okay, I'm gonna push on the elephant's rump this direction. Okay? I'm gonna hold this, and that little dot right there, is that dot, when I push on it, is it gonna go left, right, up, or down?
I just, you know what? I wanted to guess without even thinking about it.
Does anyone know? Or in towards its mouth. Oh, you think it's gonna go in? Okay. Any other guesses?
They're gonna come like towards us.
No, it's gonna stay in plane. It is gonna stay in plane. Okay, so we'll continue here.
Please do.
I'm gonna say like up and in.
Okay, up
And
and in.
I kind of feel like that because like that would be a logical way for an elephant to hold
Okay,
its
yeah,
trunk
okay,
more than
it's
that.
sure, it's
But
a
also
good
because
point.
like if this is all going over, they feel like this is gonna kind of extend there, and that's gonna get pushed up in there.
Good thinking.
Well, I don't know. Is that good thinking?
That's, well, it's thinking at least. So this is designed so that when you push on that, it actually just rotates in space. It doesn't move at all.
I knew you were gonna pull some sort
It's
of
a
trick
trick
on me.
question.
Now, since I was
You didn't
fooled by
give it
it,
as an
I had to
option,
try it
right?
out on my friend, the physics girl.
That's so trippy. That is so cool. I don't understand. What?
It's modeled after the mechanisms you use in wind tunnels, where you want to have, say, a model that's attached here, but then you move it, and all you want to do is control its angle and not.
Hey, what's going on here?
What do this saddle...
Okay. How do I advance this here?
Cool. I don't understand. What?
It's modeled after the mechanisms.
Demonstrate that compliant mechanisms are capable of producing very precise motion, which I personally found pretty counterintuitive because these objects are made up of flexible parts. But maybe that shouldn't be surprising, because compliant mechanisms don't suffer from backlash, for one thing. So backlash occurs when you have a hinge, which is basically just a pin in a hole, and it's moving in one direction. And now, if at some point the motion reverses, it doesn't happen instantaneously because there's some give in the hinge. This also causes wear and requires lubricant, and that is why compliant mechanisms have better performance than their traditional counterparts.
This one, though, is my favorite.
That is one of my favorites too. It's just so pleasing. Right?
That sound is so satisfying.
This actually, believe it or not, was inspired when we were doing things at the microscopic level, where we're building compliant mechanisms on chips. And we had to be able to make these compliant mechanisms out of silicon, which is as brittle as glass. And if you're trying to make something like this out of glass, right, it's crazy hard. But that also means once we figured out the design, we could make it in a material even like PLA, which is also, you know, not the ideal compliant mechanism material. So you can get on our website and get the material and get the files to make this yourself.
I'll put a link in the description.
Yeah, that also has a nice feel and a nice snap to
It
it.
has a really nice snap. I like when it comes out, it's like gunk. You know, like there's something about that that's really just very pleasing. So these things actually move?
Oh yeah, yeah, yeah.
I need to see this.
Okay, all right, we'll do it.
That's the
Were
NIMS
those
device right
etched
there.
on there?
Yeah,
What's
those are etched, and so just using the same processes used to make computer chips.
So another advantage of compliant mechanisms is that they can be made with significantly smaller proportions because they take advantage of production processes like photolithography.
And we have motion that we want at the microscopic level.
That's brilliant.
Plus, since they simplify design, compliant mechanisms are much more portable, meaning lightweight, which makes them perfect for space applications.
This here is something we did with NASA making a hinge that could replace bearings for, say, deploying solar panels. This is titanium, 3D printed titanium. But what's freaky about it is you get that motion, which people expect, but there's a piece of titanium that can bend plus or minus 90 degrees, 180 degree deflection.
That is solid titanium.
That is one piece of titanium that is 3D printed.
There's no alloy, nothing to make it flexible.
Yep, this is, yep, and even freakier than this is this guy right there. So that looks like a crazy beast, but every part in there has a purpose. All these flexible beams, here are the two inputs. And again, we did this with NASA for thruster application, where you can put a thruster right there. And now, with our two motor inputs, we can direct that thruster in any direction. That titanium device moves that, and you notice that it's just all bending.
It's all solid state too.
And there's no pinch points for the fuel lines or electrical lines coming in.
Here, this single piece of titanium allows you to use one thruster in place of two. Okay, that is a clutch. So the idea is, if you spin it up really fast, because it's flexible, this outer part will actually start coming outwards. And then if there's a drum around it, it'll contact with that drum and spin that thing.
Oh, so this like kind of that kind of comes out like so,
So
and
it
then
gets spinning really fast, and then you essentially engage this outer drum. So this is like the way that a chainsaw would work or something like that, because you get it spinning fast enough, and then it engages the chain, and then it turns it over, and then
force. Yeah. Wow, that's cool.
So here, this is made in plastic so that it, you can see it. But in reality, it's got to be a lot stiffer. So here it is, made in steel.
So hang on, you're saying that thing, which is made of steel,
Yep.
you spin it up to a certain speed, and then it expands and engages a drum that's
Yep.
around it.
Yep. So idle with no motion, but then at a certain speed, that are what we designed it for, it'll speed up to that RPM.
You speed it up and it engages.
Yep.
I had no idea.
Of course,
Like,
it's using
I
this
have
centrifugal
learned something
force.
today.
So let's come back to the safing and arming device for nuclear weapons. Its purpose is to ensure that no random vibrations, say from an earthquake, inadvertently disable safeties and arm the nuclear weapon. Now, one of the requirements was that this device be made as small as possible.
They had made those as small as they possibly could using traditional methods, even using things like what the Swiss watch manufacturers were using.
With compliant mechanisms, they produced a device out of hardened stainless steel, where some components were the size of a human hair. This is high-speed video. Here the device is operating at 72 Hertz, meaning this little hole makes 2 complete revolutions each second. The way it's meant to work is an arming laser shines on the rotor wheel, and when the proper input is given to the system, the wheel rotates a notch. If all the proper inputs are given, then the hole lines up with the laser beam, and crazy things happen from there. So it is essential that this device's performance is perfectly predictable, even if it sits unused in a silo for decades.
So, are these now being used on nuclear weapons?
It turns out they don't tell us what they do with the nuclear weapons. And so we designed them, we made prototypes, we tested them, and then it goes what they call behind the fence, and where it's all classified. And, we don't know what happens. So.
Hey, hey, this
Yes,
episode
that's
was supported by
basically it.
viewers like you on
So,
Patreon
yeah,
and
lots of
by
interesting
SimpliSafe.
stuff
Incredibly
that you can do
effective,
with
reliable.
compliant mechanisms. And like I said, we can all do that with ComSol. You guys can design your own. This guy featured in this video, he has a book called Compliant Mechanisms. He talked about it at the beginning. And I have the book, and we can take a look at a lot of the other kinds of devices he has in there to inspire you guys to tweak them or come up with your own kind of designs. Kind of interesting stuff. But like it says, there's like really great benefits to those kinds of things. And because of that, they're very reliable, inexpensive, and quite accurate. You don't have the slack to worry about. Lots of benefits. So, it's moving on. So, what are MIMS? Okay, so you just saw an example of a couple of compliant mechanisms that were reduced down to the microscale. So, MIMS, micro electromechanical systems, these are actually multidisciplinary, right? Micro is the scale, but electromechanical are the two domains, but also include other things. You have thermal, you have fluidics, and many other domains as well, not just electromechanical. So it's the integration of mechanical elements, sensors, actuators, and electronics on a common silicon substrate through microfabrication technology. And here's some examples, like a MIMS micro pump. Here's a micro gear right here, micro mirror device, headset display, fluidic channel right here. You can do some mixing and things like that. One way to think about MIMS as well as an interface between the real world and the virtual world. Okay, so here's human body, right? Here's sight, but if you think about it, well, actually, if you examine all of your 5 senses, touch, sight, taste, all of them, they're actually composed of micro electromechanical systems, except instead of being made out of silicon, it's made out of biological matter, right? But it's microscale, right? It's also electromechanical. And so our eyes are not just one sensor, they're actually millions of sensors. Our nose is not one sensor, it's millions of sensors. Our tongue, our ears, there's millions of little sensors just to enable us to hear, right? Our skin, there's millions of touch sensors all throughout. So we're actually comprised of millions and millions of MIMS devices in our body, biological MIMS, to enable us to have our 5 senses. Okay, so this is also enabling other things too, like robotics today. So it enables sight. Here's some types of microsensors right here. Balance, like gyroscopes, accelerometers, audio, fluidics, biochips, micropumps. Smell, chemical sensors, focus, right here, taste sensors, speech, pressure, touch, all kinds of things in our communications as well. Here's some other applications: pressure sensing, inertial sensing, optical transmitting, biological and medical, energy transduction, like harvesting energy from the environment, radio frequency stuff, and a whole lot more. And in fact, our cell phones would not work if it wasn't for MIMS. So there's lots of signals out there of different frequencies, but the thing is in order to pick out your frequency that you're talking on from all the other thousands of others, you have to have really good frequency selectivity. Okay, so for example, let's draw like the frequency response. So a typical frequency response of electronics, you might have a Q of about 10 to maybe 100, but for MIMS, because they're mechanical, you can have a really, really extremely high Q that is on the order of 10,000, a million Q. And remember, Q is basically the width right here over the frequency. Okay, so I'm sorry. Other way around. So this value right here gives you an idea of the amount of energy lost per cycle as things are vibrating back and forth. Okay, having a very high Q enables something to tune into to a particular frequency and filter out frequencies that are right next to it, right? And that's how you get your really high frequency selectivity. And also, you get really great signal to noise ratio as well, because having a high Q, you're able to get with very little energy, you're able to get it to have a very high amplitude of oscillation as well. But you get that with MIMS. Okay, you can't get that with electronics, but you can with MIMS. So it enables our cell phones to work. There's other things on there too. Like for example, when you take your cell phone and you rotate it 90 degrees and that picture rotates, it's because there's a MIMS accelerometer gyro in there that's sensing its movement. I don't have my smartwatch on today, but so for example, if you have a smartwatch, if you tilt it up and look at it, it knows what direction it's headed in, right? And so then the display will show the time will switch because it'll think you're looking at it. There's just many other things too, all due to MIMS making the cell phone possible. Also, there's lots of MIMS in your car. There's over 100 types of MIMS in your car for vehicle stabilization, to prevent rollover. It's in your airbag. It's checking pressure, tire pressure. They're all over the place. The word that's used often is ubiquitous. You know, it's everywhere. You really can't see it because they're so small, but they're everywhere. Okay, and this is what I was talking about last time about that projector when I was talking about the little squares you see on here. Those are from these mirrors right here. So this is called digital light processing. And so these are little MEMS mirrors right here, and they have electrostatic forces causing them to tilt, right? And they have little spring hinges. And so this is what a few of them look like. If you zoom out a little bit, it's like this. And this is how the whole system works. You have three colors right here. It could be white light coming through a filter, like a spinning filter, or you could have separate red, green, and blue light coming through here. You have some optics. This DLP chip right here has the million micromirrors, and they're turning on and turning off the type of light that's shown right here. So this little square right here is white, so basically it's shining all three colors, right? Because all colors, you get white out of that. This right here is black, so that right there is staying constantly tilted away, and so no light is shining there, right? To get red, every time the red coat goes through, it shines red there. So that's how that works. This is spectroscopy that's done using the same thing. So here's some light source, here's your sample, okay? Here's a slit here, it goes through a diffraction grating right here, and then it shines right here. This right here is your micro mirror display, and you're able to pick off certain frequencies. Do you guys know how a diffraction grating works? Anyone who does not know? Okay, I'm trying to remember. Okay, so diffraction grating. Okay, so let's say you have a diffraction grating can work with light incident above or passing through. Either way is fine. This slit right here, we'll do it with it passing through. It doesn't make that much difference, but this slit here, let's call that D. And you want D on the order of the wavelength of light that's coming through there. So let's say you have some waves of light coming through here in this direction. Once it passes through this this slit right here, if this distance is on the order of the wavelength of this, then what comes out are spherical bands that are like this. And another one right here comes out, these spherical bands. Now the thing is that you have these interference peaks right here, and so far away you have your plate where you're going to analyze this, which is like maybe right here, and depending on, like, this right here is like an angle of 0, but over here maybe your first maximum. So you're going to have interference fringes where you have light bands, dark bands, light bands, and it keeps on going. So maybe this theta 1 is going to be your first peak right here. Okay, that's theta 0. And then you have other ones too. Now, every type of material, every type of material gives off its own frequency. So what you can do is, just by analyzing the spectra of any material, you can actually tell what's in there. Right? So for example, let's say in a few years, one of you develop a diffraction grating that can go on your phone, such that when you're in the grocery store, you can scan some food to make sure that it's the date's right, or there's any microorganisms on it, or I don't know. Or if you're testing the water, let's say you're testing water, right? And you want to find out what the constituents in the water, you can do this type of test, and maybe one of you will develop a way to actually figure out, on a cell phone, what types of things are in the water, or what's in the air, or just wherever you aim it to, right? This is how we determine what's in stars. We examine the starlight that comes through our telescope, and we're able to determine what stars are made of, even though they're millions of light years away. I remember correctly, this angle right here, how's that go? I think it's something like this. Like the D between both of those, I think it's like D sine theta, or whatever the mode is, that's 0, 1, so on, is equal to m lambda. And that's the mode. It's some kind of equation like this. Probably from Snell's law. Right? And that's just what's used to get this. Now, in this particular case right here, they're zeroing in on a particular mode. So they have one little photodetector right here, because that's all they're interested in. Okay? Because maybe they're looking for something very special. But anyways, that's what they're using that for. Now here's a MEMS resonator, and we're going to talk about the cantilever today. So that's these things right here. So this is a comb drive. I'm going to talk about a little bit about that in the coming lectures in today. On the cantilever today, this is a folded flexure. This device is anchored to the substrate right here and here, and everything else is floating above the substrate. So if you use your imagination, you can see this thing sort of like is able to move back and forth this direction quite easily. Okay? And these flexures are able to bend to allow it to move. The thing about compliant mechanisms is that even though it's all the same material, you're playing around with the compliance of the material, right? This is silicon, that's silicon. But this silicon is very thin, so it's very flexible. This silicon is very thick, so it's rigid. Or you're approximating it as rigid. Okay? So you're playing around with geometry, sizes, and the material properties to try to get things to behave the way you want. Also, what's really interesting about MEMS is that this material is also conductive. So you have two things happening. You have the mechanical behavior of this thing able to oscillate back and forth, and then because it's conductive, you're able to apply a voltage between this side and this side. And if you have a voltage, like if this is high potential, that's low potential, you have positive charges and negative charges, and what will happen is that it'll attract each other like that. So this comb drive is able to get pulled in by just you applying a small voltage across here. Okay? And hence the electromechanical behavior of MEMS. This is what it looks like if you try to simulate it in COMSOL. What you see here was plotted is the voltage potential. This is the field right here. So here's a comb drive. This one is not smooth. They purposely put these ridges on there so the capacitance will change as the fingers slide past each other like that. Okay, but you can see here's a cantilever beam, here's a cantilever beam. This part's kind of thick, so it's more rigid. This right here is anchored, and this thing right here just moves back and forth. So this is a half of it, the other half is over here, but you don't see it. Nice thing about MEMS too is that you can sense capacitance quite well in MEMS. And so as the fingers come together and engage, there's a change capacitance. Capacitance gets larger the more overlap you have with the fingers. So what happens is that you're able to tell the position of this just by monitoring the change capacitance, how it's moving. So even though it's really tiny, you can barely see it, you can determine how it's actually moving. Okay, so let's look at scaling laws. So this right here is a cantilever, okay? It's anchored right here, here's a free end, and maybe you have some force pulling on it. We're going to derive these in another lecture, but here I just want to show you what the basic forms of stiffness, mass, and maybe some electrostatic force is. So stiffness is 3 EI over L cubed. This I right here is the second moment of area. This is the Young's modulus. It's a material property, and L is the length of the cantilever. This I right here is right up here, it's like absorbed at 12. So the second moment of area is the layer thickness, the width of the cantilever cubed over 12. So if you plug this in for I, then you get this right here. Mass, you're looking at the effective mass, right? Not the whole mass, because this piece right here doesn't really move as much as the mass on the tip, right? So it turns out to be 33 over 140, the density times the volume. Layer thickness, the width, and the length of that beam. The force of cone drive, you can get this from Maxwell's equation. Basically, is 1/2 the change of capacitance with respect to displacement and voltage squared over the comb drives. And this derivative right here, this partial derivative, it equals this stuff right here, if you work it all out. Okay? The 1/2 and the v squared is carry over. So, for scaling, if you look at stiffness, you can clearly see that the things that can scale are things that scale by length. So you have your layer thickness, your width, and your length. Okay? So, for example, if you have this thing that was at a meter scale, and then you reduced it in size to microscale, which is 1,000,000 times smaller, you can see what happens here. So if you have this layer thickness, and let's say it's 2 microns, or let's say it's 2 meters, sorry. And then you scale it down by S. And S in this case is going to be micron, 1,000,000. Same thing with width. You know, maybe that's 4 at the meter scale, and you're going to multiply by S, and then S is a micron. And same with length. That could be, I don't know, 200 meters, and you're going to scale it down by this factor of S. and that's a micron. So if you look at the dimensions of this, the numerator has this s appear 4 times. 1 here and 3 times in there. So s to the 4th. Down here, you have s to the 3rd. So s to the 4th over s to the 3rd, that's just going to be s. So that means that if you reduce any cantilever down by a factor of 1,000,000, the stiffness is going to reduce by 1,000,000. Okay? Let's look at mass. Mass has nothing on the denominator here. It has H, W, and L all in the numerator. So if all of these things shrink down by 1,000,000, what's going to happen with mass? How much is it going to reduce by? What was that? I didn't hear that. 1/3? Well, you're close. The 3's in the wrong place. It's in the power. Yeah. So it's going to be 1,000,000 to the power of 3. So we're talking 1,000,000 has 6 zeros. You raise that to the power of 3, you're going to end up with 18 zeros. Does anyone know what number that is? Quintillion. So, which is really interesting. So your mass reduces by 1,000,000,000,000,000. A quintillion. Think about that. That really changes the physics, right? The stiffness only reduces by 1,000,000. The mass reduces by 1,000,000,000,000,000,000. That's crazy. But that's what happens. Let's look at what happens to force, okay? So force right here, let's look at the geometry. There's a gap between the fingers, so that's going to shrink. There's the layer thickness, that's going to shrink. So you have one S contributing right here, another S contributing right here. So what's going to happen with the force? It's constant. It doesn't change at all. That is weird, right? You can, so for example, let's say, let's say there's a potential difference between the wall and myself. And there is, right? Maybe I'm at, 10 volts and the wall's grounded at 0 volts. Okay? There is an electrostatic force between me and the wall. But I'm so massive, I'm on the meter scale. I haven't reduced my size down yet, right? My stiffness is pretty much, massive as well. So this force is so negligible at the meter scale. But if we take me and the wall and we reduce our size down by a factor of 1,000,000, my mass goes down by 1,000,000,000,000,000. My stiffness goes down by 1,000,000, so I'm more flexible, right? But the force remains the same. It's just as much force that I feel at the meter scale as at the micro scale. But all these other things have reduced drastically. So what happens is that this force, which used to be negligible, can dominate, be much stronger than gravity. Okay? So this is the reason why really strange things can happen with MEMS that you just can't, it's hard to achieve in real life. I mean, in real life, it is real, but it's hard to achieve at the meter scale, which you can achieve at the micro scale. It even gets weirder at the nanoscale, because then you have quantum effects. Okay, so let's look at how stiffness is combined here. So here's stiffness right here. Here are two of these beams right here. So if I have 2 of these right here, then what's going to happen is that I'm going to stick a 2 right here. So this stiffness becomes this. Oh wait, the 3 got absorbed. So 3 HWQ over 2L. So that 2 is in there. Okay? So that means that the stiffness goes down quite a lot just by extending it. Now if I double up this right here, then what happens is that the stiffness felt right here is 2 of these. Okay? Now if I do it this way, where I apply a force here, I'm going to get twice the deflection as I got right there. So if I do it this way, the stiffness reduces by a factor of 2. Okay? Remember, this one right here is 2K1. This one right here is 1/2 K1. Okay? Now, if I do it this way, right here, this piece right here is like this. These two are like this. So what happens is that it cancels out. I'm doubling it right here, but I'm halving it with that. So this right here has the same stiffness as just one of those. Okay? And then of course this over here is doubled. Right? So that's how the stiffnesses add when you combine them together. This right here is atomic force microscope. Okay? And you can see here is basically a cantilever, and you drag it over the surface. This is the reason that the revolution in nanotechnology took off back in around 86, 87, is because this was invented. It was the first time we were able to see actual atoms, or at least the contours of the atoms on surfaces. Okay, so it works by having a cantilever. It's fixed right here. You shine a laser beam off of that. You have a photodiode, and as the tip moves up and down, it changes the angle of this light on the photodiode. Okay, and this right here is the tip of the cantilever right there, the tip, and you have all these nanowires, and they're just pushing them over. Okay, that's what they're doing. But again, the power of the cantilever. It's really important to know those kinds of things. Okay, so let's talk about how MEMS are made. Okay, so let's look at the colors here. Blue right here is a substrate. So think of this as a cross section of a silicon wafer. So you have a wafer, looks sort of like a CD, but if you break it in half, look at the cross section, it looks like this. Where this is a substrate, and then to get things ready, they deposit some oxide, some silicon dioxide right here, which is the insulator. They deposit some other oxide right here, and then they deposit some other silicon right here. This silicon is conductive, and then they also deposit some glass up here. Okay, so the whole wafer is covered with these different layers. It's not even a scale. This right here is like 300 microns. Okay, this right here is like 2 microns, so it's not really the scale. So first, what's done is you could deposit some metal, and you do that by applying some photoresist on this right here. And photoresist is really interesting. It's a polymer, and if you shine light on it, the bonds are broken, and then you can develop it with some. They have chemicals that allow the areas that have their bonds broken to wash away and leaves behind the areas where the bonds are intact. So what you can do is this. You can sort of like, here's your top layer right here. You deposit some photoresist. You have an object in there to cause some shadowing. You know, sort of like, you know, here's an object that causes some shadowing. You shine light on this thing. The light goes through here, and it breaks these bonds in here. And then you remove your mask, and then you put you develop this, and what happens is that only this part washes away. Okay, that's how you're able to expose part of the surface and protect the other part of the surface. Then once you have that, then you deposit some metal on this thing. So metal goes on the whole thing right here. Metal goes right here, and metal goes right here. Right? Then what you do, you then put some other developer in here that gets rid of this part of the photoresist, the part that actually has the bonds intact. And so that's washed away. And so what you're left with is that. A lot of steps just to get that. Right? So that's how it's done. Okay? That's how that got there. The next thing you do, again, you play around with your photoresist, you protect these areas, you protect this little top area, you protect this area. These are the holes where the light came through and broke the bonds, and then you etch this stuff out right here. Okay? Then the next step is you etch out the backside, right here. Remember, you have like 300 microns, maybe 400 or 500 microns to etch through. So you etch all the way through the backside right here, and you protect this. So you put some protection material on it to protect that so that doesn't get etched away. And then once that's done, you etch the rest away, and now you have your cross section of your MEMS device. This could be like a cantilever. It could be all kinds of devices, but this is just a cross section of what that looks like. Okay. Here's another process right here, where here's the silicon wafer. First, you deposit some insulator, then you deposit a conductor in blue, and then another insulator in purple. Then you deposit some sacrificial material that you're going to take away pretty soon. But you have that there to make some space between the top and the bottom, because then you're going to put on your cantilever. So there's a cross section of a cantilever right here. Then you put it into a chemical that washes only that orange material away, and now you have a freestanding cantilever. Okay, so that's a really quick overview of how things are processed in the lab. We actually have a course here at Auburn that goes over all this in great detail. Okay, so here's some MEMS and its simulation. So this was done by a colleague of mine. It's a micromirror. These right here are comb drives. There's like 1,000 of them. And when you apply a voltage across on these comb drives, it creates a force. And this force yanks on this tether. That tether is attached to this sort of like U-shaped thing, and it creates a torque about this cantilever right here. And then that torque causes this mirror to rotate back and forth like that. Okay, this right here is a top view of that. Okay, so you can see this U-shaped piece right here. You can see the tether right here going all the way back and attaching right here. And this piece right here is kind of blurry, but it's a perforated cantilever that rotates like that. Okay, so the whole thing is like rotating like this. Here is something I did to model this using compact models. Okay, so this is all done in MATLAB. And this takes a long time to fabricate. So we're talking like, it could take weeks to months to get it just right. Okay, this right here took a couple of hours to put it all together and design it, put it all in there. But then to simulate it is really fast once you have the design in there, and then you're able to parameterize different things. So this axis right here is the beam width. This axis right here is the moment arm length right here, and this right here is the angle of it tilting. So clearly you can see if you wanted to tilt the most, here's the sweet spot right there. Okay, and here's experiment versus the software. Experiment in red, software in blue. Here's some other things you can do with cantilevers. You can, well, the actual model of the cantilever, you can tweak the parameters of it and have it behave like all kinds of things. Like, for example, the carbon bonds in nanotubes. This is all made with cantilevers. right? This right here is from a researcher from, well, the design is from a researcher at Northwestern University, where they're making a sort of like a nanomechanical tester. You have those thermal actuators. You have a carbon nanotube right there, and you have some flexures, cantilevers right here, and you have some comb drives right there. And so I designed that off of his design. Here, this right here is another device using carbon nanotubes. Here's something that was actually made in the lab, and it's just simulated using the tool. So here's a GUI of the tool I'm talking about. It's called Sugar Cube. Like I said, it was all programmed in MATLAB. Here's one of the designs right here. Here's the output. So basically how it works is that you either start off with a new configuration and you create your net list, and that's basically a text description of how all the parts are going to connect together. And all the parts are cantilevers. So I guess you could think of today as a cantilever lecture. Then for your design, you can like pick your process file where that tells the tool what is a Young's modulus, what is the coefficient of thermal expansion, just all your material properties. Then you, here's some modeling right here, and then you simulate it. You can do static analysis, modal analysis, frequency, or time domain analysis. Here's another one where this is a atomic force microscope. Here's a probe tip. Here are like two cantilevers holding it. And here I'm doing like a Bode plot, but I'm manipulating a couple of parameters while I make that plot. In this example, this is supposed to be the DLP. So this is like the micromirror. All of them are getting random signals. That's why they're all, they're just flipping around in different states. But here's a model of that. Here's this thing called, I call it a microid. So basically it's like a micro robot that has insect-like dexterity. So it has these little piezoelectric legs. It's able to move around. It's able to walk. This could be like the CPU. That could be like the battery. What's really cool is that this works at the microscale, but if you try to enlarge it to like the size of, I don't know, the cell phone, it wouldn't work. Lots of things happen once you shrink things down. Remember, like the mass gets really reduced, and that enables this whole thing to be supported quite easily with these very thin legs. This right here is like a honeycomb structure. This is what the net list looks like right here. This whole net list right here made this entire structure. So basically all I'm doing is I'm making like one of these, and then I'm having it go through an array, rows and columns. Just making lots of them. So you just make one and make as many as you want. They're all connected together. So this right here is an example, of me like using it real time. So this is the width of a nanowire. These are the thermal actuators right here, and the flexors, comb drives. So what I'm doing here, I'm like changing the parameters of the net list. So the net list was that text you saw before, but each parameter of net list, you can change it with some sliders and typing in new things. So it takes the complexity out of it. So you don't have to make it once, but then you can change the design around to many other variations just by changing the parameters. And if you sweep parameters like I've done here, you'll be able to make a parametric plot from that. There's some other things that are in there in the file. Again, it's all based on cantilever, everything you see here. So, how long do I have here? Well, it just keeps on going on. Let me see here. So, it's only like 5 minutes, but yeah, that's the nut list right here for this heatuator. Yeah, we only have a few minutes left, so that's why I'm like just trying to zoom through real quick. Yeah, I'm just doing different parameter sweeps for this kind of structure right there. I just loaded up. But anyways, again, that's all in MATLAB, and is using electrical and mechanical elements. Okay, so for our last 6 slides, let's go through ODEs. Okay, so ODEs. Okay, so I know many of you already know this, but let's just go over it anyway. So the order of an ODE is the order of the highest derivative. Okay, the degree of an ODE is the power of the highest derivative. Okay, but this is only for polynomial equations, so not for something like this. The linearity of an ODE is the linearity of the dependent variable and its derivatives. Okay, so let's go through a few exercises. Okay, so for this equation right here, what's the order of this ODE? Yeah, first order, right there. So y is the independent variable. Okay, I'm sorry, the dependent variable, x is the independent variable. So what about this equation? What's the order? Yeah, 4. The highest derivative right here is 4. This doesn't really count, right? You know this is raised to the second power. If this wasn't here, that term wasn't there, then the highest derivative would just be 2. I mean, so the order would be 2. What about this equation? What's the order of this ODE? Yep, 3. Highest derivative right here, 3. And what about this one? The order. Yeah, 2. Okay, so let's do the degree. So what's the degree of this one?
1.
Yep. The power of this is just 1. What is the order of this one?
4.
4? I'm sorry, the degree. I said order. What's the degree of that one? Yeah, 1. This can fool you, right? Because this, I mean, the order, the degree of that is, of this alone is 2, but the degree is the power of the highest derivative. Highest derivative is right here. What about this one right here? The degree. Yep, 2. Somebody said 2. And we can't do it here because it is now a polynomial type of equation. Now for linearity, let's go through that. Is this linear or nonlinear?
Non-linear. Oh, linear.
Yeah, it's linear because you're looking at the dependent variable, right? So that's linear, that's linear. This right here, the coefficient does do some weird things, okay? But the dependent variable is linear. What about this right here? Linear or nonlinear?
Non-linear.
Nonlinear because they had 2 on that dependent variable. What about this? Linear or nonlinear? I thought this was easy for linear. Well, it's nonlinear, yeah, nonlinear because you see, I mean, all of them. This is raised to the 4th power of those, and that's raised to the 2nd power. What about this right here? Linear or nonlinear? yes, nonlinear because of the cosine. Yeah. So, anyways, that's that. So, but this part right here is important for today because we're going to look at the order of ODEs. One thing you need to know, if you want to simulate ODEs, you have to be able to convert an nth order ODE to a set of first order ODEs. So we're going to learn how to do that right now. So here's a fourth order ODE right here. Let's say that was given to you, and you want to simulate it by, say, throwing it into MATLAB. So you got to convert this to this right here. So what you do is you can rewrite this as this. And the only reason I did that is just because so I can show the numbers right there. So if you have a number in parentheses, it's not raised to the power of 4, it's the fourth derivative of that, okay? Third derivative, okay? So then what you do here is put all this stuff right here on the right-hand side and put the highest order on the left-hand side. So that's what this equation is right here. And then you take this equation and you make a set of equations. If this is fourth order, you're going to end up with 4 equations. So what you could do is just take this variable, which is x2, which is x with the third derivative, just turn it into x3. It's a new variable called x3. It's unrelated to, it's not x, okay? It's x3. I could have called this y, I could have called that z, I could have called that u, okay, by just calling it x3, x2, x1. So I have all the numbers matched up, okay? And this right here, this is x, the fourth derivative of x, and I'm going to call it x3 prime. So it's the first derivative of x3, which is really this right here. And what I mean by that is that this, wait a minute, yeah, that is the same thing as this. 1, 2, 3, 4, same thing. That's all it's really saying. So this right here is this. And then once you have this equation right here, the other things are just easy. They just drop in. So x2 prime is just x3, x1 prime is just x2, and x0 prime is just x1. Okay? So all of these are all single. Here's your equation right here. These are all algebraic variables now. Okay? They're not derivatives. They're actually new variables. But if you were to like take this and substitute that in there, you can take all of these and put it back in there, and you end up with this equation. Okay? But here's the set, and it's just a first order equation. So these are all first derivatives. Everything else is right here. We could do the same thing with a mechanical equation like this, which is just a second order. It ends up being like this. And this is what we'll put right here. So in MATLAB, you do it like this. So in red, that is this equation right here. Where I took this second order equation, I rewrote it like this, and I stuck it in right here. Okay? Everything else are just parameters. Okay? I'm going to say what the mass is, the stiffness, the damping. Here's where I call the ODE. This is the solver. This is the name of the this function right here. It's called ODE. It's the span, the initial displacement, initial velocity. That goes in here. The MDK is this thing right here, and that's how I'm passing these values into this function. I got to call them back out again, and then throw them into my differential equation. So this just is what's integrated, this equation right here. And if you look at the plot, this is the thing I'm simulating right here. This is just a microshutter. Oh, wow, what time is that? Okay, I'll go over it very quickly. This is a microshutter. So basically, it looks sort of like, just think of it like a shutter on a window, right? Lines on a window, right? If it's like this or like that, opening and closing. So this is right here where it's closed, and then if I deflect it to the right, it opens up and lets light shine through. Here's the waves of light shining through, where if this is closed right here, here is open, light's able to shine through. Here's what's happening down here. And here's my simulation I get from running the MATLAB solver. If I have a linearly increasing voltage, it just comes down right here, it makes contact and it stays. If I have a sinusoidal, it just grows like that before it makes contact and stays. Here's a really interesting one where it tries it over and over again before it stays. But yeah. So anyways, this is using this thing right here. That's all I input in order to try to simulate this. I have the overall stiffness, I have the overall mass, and I just put that into here and here, and I just guessed what the damping is. Okay. So, anyways, yeah, 2 minutes over, so I better get you guys out of here. So, that's it for today, and hopefully Thursday we'll start ComSol.